All right. Hello, everybody. All right. My name is Jeff Barr. I'm the web services evangelist at Amazon.com. In the next hour, I'd like to talk to you about a really cool new product we have called the Alexa Web Search Platform, or AWSP. This is my agenda. I'll talk in general terms about the Amazon Web Services. I'm going to start with a little bit of a history lessons. As I was preparing this talk, I was thinking about how much easier it's become to put together a website in the last 10 years. From there, we'll move on to the body of the talk, how to use the Alexa Web Search Platform to build your own search engine. And then, as time permits, we'll do some Q&A. And if time doesn't permit within the session, I'll certainly be available afterward to talk to you. Let me give you a bit of background on who I am. I've got a software development background. I've been building software since I was 18 or 19 for pay, so definitely more than half my life. I spent time at a couple different startups. I've worked as VP of engineering or CTO at several different web services startups over the years. I spent about 3 years at Microsoft on the Visual Studio team, worked on Visual Basic 6 and Visual Studio.net, the first release, worked on technologies like HTML, XML, and some very early web services work in the first generation Visual Studio. Left Microsoft to do some consulting with various startups and venture capitalists. And one of the things that we worked on back in 2000 or so, we had a lot of different companies. I was working with some VCs, and we were looking into the web services space. We draw some neat diagrams about how we had the web, and we had our tools, and these applications people could conceivably build. And we had this theory that these applications could actually connect up to the public web and to public web services. But those didn't really exist. So we would draw this big cloudy picture and say, sooner or later, there'll be some actual web services that our applications and our tools could connect up to. People didn't really buy that story back then because it was just this big, not too well-defined cloud. And they'd look at us and say, yeah, sure, that doesn't sound like the most plausible future at this point. So after doing that for a couple of years, I saw what Amazon was up to with web services. I saw the first beta test of the Amazon Web Services in early 2002. I saw that and suddenly realized this is that cloud that I've been drawing for these last couple of years, but it's actually a reality at Amazon. So wanting to do something that was more based in reality than based in some clouds, I decided to sign up with Amazon and do everything I could to help move the web services effort forward. I've now been at Amazon for over 3.5 years, and in my job as the Amazon Web Services evangelist, I get to travel all over the world. I meet with software developers in meetings large and small, and I really enjoy meeting with developers and sharing all the fun things that we're doing with web services. Has anybody here not heard of Amazon? Anybody here not shopped at Amazon? Raise your hand. Cool, okay. How many of you have heard of the Amazon Web Services in the past? Okay, about a third or half or so. So we're best known as an online retailer, and in that capacity, we have over 55 million active customer accounts, and by that I mean people who have actually gone to the site, made a purchase, and successfully checked out in the last 12 months. We have website presences in 7 different countries, the US, UK, Germany, Japan, France, and Canada and China. We're not so well known, however, as a very intense technology consumer or as a technology provider. We're a great technology consumer with the operation of all these different websites in all these different countries. You can imagine that behind the scenes there's just vast amounts of computational power. We've got actual physical website presences in data centers located around the world. We have huge data warehouses. In one of our main business data warehouses, we have over 25 terabytes of data. We have world-class logistics behind the scenes so that when you place an order with us, we can get that order to you as inexpensively and as quickly as possible. We actually operate 21 different fulfillment centers representing 9 million square feet of warehouse space. And then finally, we're also a very, very strong technology provider. We use our technology with Amazon Associates. Hundreds of thousands of associates use our technology to pull products from our catalog, put those products on their website, and then earn commission from the traffic that they send us. We have over 1,050,000 Amazon seller accounts. The sellers use our technology to compute prices and determine proper selling prices and time frames for products that they can list and sell on the Amazon platform. And then finally, we have over 150,000 software developers registered in the Amazon Web Services Developer Program. We have a subsidiary company, Alexa. They've been a subsidiary of ours since 1999. They do several different things. They collect web usage data using the Alexa toolbar. They do various web crawls and collect and compute web metrics and traffic rankings. They operate a very large, very busy data center, and we'll talk about that in quite a bit more detail in just a few minutes. Okay, the Amazon Web Services are a set of APIs that give developers programmatic access to our data and our technology. So you can think of the retail website as the consumer interface to Amazon.com, and then the Amazon Web Services and all those APIs as the developer interface. We have 8 different public web services at this point in a number of different categories. We've got building blocks, we've got the exposure of web scale infrastructure, some of the things I'll talk about today, e-commerce capabilities with our e-commerce service, rich content, rich data, information about various products in our catalog. We can use these services to create various new business models, and we even have customer-created content, things like ratings and reviews and other things that customers have built and uploaded to the site. So when you think about the theme of this conference, the MIX conference, we're the suppliers of some of the raw materials that you can take and then mix and remix and mash up in order to build your final application. We're the pantry that you go to and you open up the door and you start looking and say, I want to make something. What do I have? I got these ingredients, these other things. What can I make with these services? So take a look at the different services that we have and think of those as the ingredients, if you will, for the various mix-ups and mash-ups that you'd like to build. This is our product family. We now have 8 different web services, ranging from the e-commerce service, ECS as we call it, complete access to Amazon's product catalog. We make this service available for free. Now, one of the neat things about all the services on this page is that we make sure that we have a business model behind each one. We do see web services as an integral part of Amazon's future, so we're very, very careful to make sure that when we give out these services, there's actually some reason for us to do so. This isn't some kind of an experiment or some kind of science experiment that we're just doing it just because it's kind of a fun thing to do. We do see this provision of web services as something we can do to drive a real fundamental shift in the way that developers build applications. So we're very, very careful to make sure as we put these services online, there's ways that we can actually make money from them, and we also want to make sure that developers are able to use them as part of their businesses. So every one of these services is also licensed for commercial use. You don't have to come and talk to us, negotiate special one-to-one licenses if you want to use them commercially. Each and every license on every one of these services lets you use the services in commercial fashion. Amazon historical pricing lets you reach back in time into our data warehouse and say, for any given product, what was the pricing last quarter, the quarter before that, the year before that? Is the Amazon sales rank, is it going up? Is it getting closer to #1? Or is it going down? Is it becoming more popular or less popular? This service is very popular with the Amazon Marketplace sellers who list and sell products in Amazon. They can use this to figure out if their inventory is gaining in value or decreasing in value, figure out the most opportune time to list their products. If they have certain products that seem to sell better in certain seasons, be it the holiday season or the back to school season, they're able to use the historical pricing service to figure that out by looking back in time. The Mechanical Turk I talked about yesterday in my session implements a concept called artificial intelligence, where you can use our APIs to put work units into our system and then make those work units available to qualified workers all around the world who can then do these online tasks and earn money. Basically, you can get a paid internet scale workforce. The Simple Queue service is an IT building block. Using this service, you can create a hosted queue within the context of an Amazon account. You can then build applications that from all over the world can, in a distributed fashion, push items into a queue and then pull items out from the other end. If you have data collection applications where you need to pull data from a number of different desktop machines, aggregate that together in some central location, you can use the Simple Queue service to do that. Our newest service is called Amazon S3, the Simple Storage System. This is storage for the internet. I'll talk about that a bit more in my next slide. And we finally have 3 different services from our Alexa subsidiary. We have the Alexa Web Information Service. It gives you direct access to the Alexa data warehouse, which consists of 300 terabytes worth of web crawl data. We allow developers to make 10,000 calls per month for free to that service, and then give you extra calls past that for just 15 cents per 1,000 calls. Within that service, you can do web searches against the crawl data. You can explore web linking. You can start with any domain name and then do queries such as, from this domain, where does it link to? Where do those domains link to? Follow those links through. Or you can say, with this domain, who's pointing at it? So perfect for search engine marketing, search engine optimization applications. Alexa Top Sites is a great byproduct of the usage data that we collect with the Alexa toolbar. Using this service, you can ask questions such as, what are the 10 most popular sites on the web? Or what are the 10 most popular sites in any particular country around the world? And then finally, the one I'll talk about the most today, AWSP, the Alexa web search platform. The idea here is you can roll your own search engine. You can build a search engine hosted on Alexa infrastructure, and you simply pay us for the CPU time, for the storage, and the bandwidth that you use. This is a relatively new service, still in the late stages of beta testing, and that's what I'll be talking about for the majority of my talk. Amazon S3 we just introduced a week ago yesterday. The simple storage system stores for the web. We introduced a very simple API to allow applications to put and get large blocks of data to Amazon-hosted, very secure, very reliable storage. You can store blocks of anywhere between 1 and 5 gigabytes at a time. And we simply charge developers based on how much they store and how much data they transfer in and out. We have what we believe are very reasonable prices for this storage, 15 cents per gigabyte per month to store data, and then 20 cents per gigabyte to either upload it or download it. Each item or each object that you store in S3 can be either private or public, with access control lists to control levels in between that. Very scalable, very reliable, cost-effective, and most of all, simple. We do actually think that S3 is a great complement to the kind of applications that you would build with the Alexa web search platform, which is why I gave you some extra detail here. All right, we're going to go a little bit into history and use this as an entree into the actual way that we'd use AWSP to build a search engine. So let's think back about 10 years and how hard it was to create a simple website and get it online. I remember actually going back thinking 1995, 1996, the first couple websites I built. It was a lot of work. And what I've found as I look back is a lot has changed, and a lot has changed, and it's now a lot easier to do that now than it was before. Some of the things that you have to do to bring a simple website online: register a domain, get DNS support, get a network connection, get server hardware, get some development tools, figure out a way to get your site popular, and then figure out a way to actually make money from your site. These things are now very, very easy and very, very straightforward now. Wasn't that way 10 years ago. What did we have to do 10 years ago to get a domain registered? We had to go pay a lot of money to Network Solutions. We had one vendor. It was a very complicated process with forms and emails going back and forth. Now it's really easy. You pay $10 or less to any number of different domain providers. You go online, a quick search will show you dozens of different providers. In 10 minutes, you can go from that great idea for a new domain name that you woke up with to finding that it's available, to having it registered, and your business is almost ready to go. Getting DNS support. 10 years ago, it was very, very hard to actually get a DNS name registered. You had to find a helpful friend or sometimes a university that would host your DNS records. There was long propagation time, so if you changed any IP addresses or names, it could take days for that information to scatter around the web. It was complicated, and I've got several books still on my shelf that are all about just doing DNS. It was a mini project in and of itself just to study and understand what it took to get DNS set up. And this was just one little step it took to get your site online. Now it's really easy. There's free services like ZoneEdit, very short propagation time, so you register and minutes later it seems like your domain is well known. And there's a whole lot less to know and a whole lot less to understand. There we go. If you recognize that noise, you're in better position than my kids. I had to use a dial-up laptop last year, and they heard all these modem noises, and they said, "What's that, Dad? I'd have never heard that noise before." But it wasn't so long ago that you could actually host a small-scale website at the other end of a modem. A little bit more sophisticated, you could use an ISDN line to your home, which a few folks did, or moving up, you had things like a T1 line, and in any case, very expensive connections. Now we've got cheap DSL, we've got dedicated hosting, much less of an investment to get going. When you need some server hardware, back then you'd start with a dedicated PC. If you really were getting successful, you call up your Sun sales guy and order 7 figures worth of expensive Sun hardware. Now you can build your own PC for a couple $100. You can find any number of hosting providers that will do a great job for you for a number that you might not even have to get your spouse to approve before you register for these hosting providers. And of course, we still have the expensive Sun hardware that apparently some people still use. And just an illustration, this is from one of the providers I use, a company called Bocacom. You can get a very, very sophisticated, very powerful machine for $100 a month. You get this great idea, you get your machine, you put your credit card in the site, and an hour later you've got a root password and you've got a machine that you can start building applications on. Quite a change from 10 years ago. Development tools. I definitely built a number of sites with text editors and shell windows. Now we've got all kinds of great visual tools, Visual Web Developer, things like HTML-Kit and Front Page. Make it a whole lot easier to have that great idea, build your application. How did you get things popular back in the old days? Well, I remember this thing called Yahoo What's New, and I remember when the web was actually small enough that I used to read all of Yahoo What's New every day so I could keep up with this web, and I could see every new site that came online. Places like Usenet, you could issue press releases, and then Wired Magazine was a great way to get some publicity. Now it's a whole lot easier and a whole lot quicker. You build something cool, you put it online, you tell the right people, they're going to put it in their blog, they're going to get some publicity from there. It's going to spread around what we see is that the old PR vehicles that even at Amazon that we used a couple years ago, in some cases, they're just not fast enough. We find now you put a new service online, you get a few bloggers to link to it, and in a space of 24 to 48 hours, you go from no one knows about you to seemingly everybody that needs to know does know about you. The combination of blogs, RSS, and pings has been a very powerful combination for us. Various link sites like Dig, and then word of mouth still counts for quite a bit for PR. All right, back in the old days, it wasn't that easy to make money. At first, people weren't even sure you were supposed to make money from websites. People kind of had this attitude, oh, gee, we're purists, we're just doing it for fun. Banner ads started to appear, and you've got that little picture there that is actually the first banner ad that I think was an AT&T ad. If you were a big site, you dealt with ad salespeople, but there was a certain minimum size you had to be before they'd even take you seriously. Now it's a whole lot easier. We have all these pay-per-click ad systems. It's totally self-serve. It's very, very easy to monetize page views. If you can build a site that's going to bring in the page views, it's almost certain you can figure out a way to make money from it. So where am I going with all this? So those were all the steps you'd have to take just to build a really simple website. Going on from there, if you wanted to actually build your own search engine, it was even more complicated. Lots of servers, lots of bandwidth, tons of software, lots of money, a lot of intellectual capital to first figure out your crawling algorithms and your data storage algorithms and your search algorithms, build your site, and then lots and lots of time. That picture on the slide there is actually one of the first Google compute clusters that's now in the Computer History Museum in San Jose. So one of the things that we want to do with our services is actually democratize this process, make it a whole lot easier for aspiring developers to build their own search engine. This was the root of the thinking behind the Alexa web search platform, and that's what I'll be talking about for the rest of my talk. So how do you go about building a new search engine now? You can use our own infrastructure. You can leverage the fact that Alexa has a crawl running continuously, collecting up hundreds of terabytes of new data every 2 months. You build on top of the Alexa web search platform. Alexa maintains a 300 terabyte archive. There's always a new archive that they're building. There's a current, fully completed archive, and then there's one archive behind that's 2 months old. Represents about 10 billion web pages and other objects on the web within this 300 terabytes, and it's fully pay-as-you-go. So you don't need to make this gigantic upfront investment in order to create your search engine. You simply pay us for the CPU time, the data storage, and the data transfer as you use it. So what we call this is AWSP, the Alexa web search platform. Its tagline is build your own search engine. Relatively straightforward process. I'm going to go through each of the steps in detail. First, you need to figure out which of the pages you'd like to process within the archive. You need to choose a particular archive, and then you can choose to process either HTML pages or pages that link somewhere, pages with specific content on them, pages that return specific values in particular HTTP headers. Once you do that, you write a parallelizable program that runs on an Alexa server. You test that in the scope of a single server. Once you're happy with the way that application is running, you reserve a number of servers from our bank of servers we have available. We give you a specific time that it's going to run, and then you run your application full bore against all the pages in the collection. Once your application has run, you can publish your results privately, you can create an XML feed, or you can even publish them as a new web service that becomes a parallel search key to the Alexa Web Info service. You can either keep that for yourself, or you can publicize it widely, or you could share it out only with your friends if you'd like. This is a for-pay service. We have a great pricing model where everything costs $1. For $1, we give you 50 gigabytes worth of data processing. What that means is that's data transferred from the archive over to your processing machine, your processing node, or you get 1 CPU hour. Once you've published data, you can get 1 gigabyte of downloaded data, or you can service 4,000 web service requests. So we tried to make the pricing model pretty straightforward and pretty understandable. Let's take a look at some of the different concepts behind AWSP before we get into the details. These are the basic vocabulary terms that you need to understand in order to build your application. An interactive node is what you use for development. So this is an actual Linux-based application. What you do is you go to the site, you reserve the use of an interactive node. We return to you an identifier for a node. You go to a web page and say, I need a machine to do some work on. Within a minute or two, it says, OK, this is the machine you have been assigned. You use an SSH client like PuTTY. You shell over to the machine, open up your account, and you're on an interactive node, dedicated machine for your own use that you use while you're building your application. The user store is a local data store that you can use for any temporary needs of your application. There's 12 terabytes of temporary storage available to your application and any other applications running in parallel with it. So we have a moderate number of interactive nodes representing the expected amount of parallel usage of people building applications. And then we have a much larger number of compute nodes that are actually used for processing. So you build your application on the interactive node and test it. Once you're happy with it, you turn it over to a bank of compute nodes to do the actual processing against the archive. And then finally, we have the data store. About 4 billion documents and each are pulled down by each of the Alexa crawls. There are 3 crawls each at 100 terabytes. The in-process crawl that's currently being built, so that one's growing, so that one would probably change every couple minutes if you were to actually be pulling data from it. The current crawl, that's the one that is complete, and then the previous crawl. So this crawler actually recycles every 2 months, and each of these old crawls will expire after 2 months. So if you are always running against the current crawl, the definition of that crawl remains the same, but there will be, every 2 months, the actual set of data underneath will go from the in-process to the current crawl. This crawl actually incorporates all the different document types you might find on the web: HTML pages, media files, images, audio, video, XML files. We also save all the document header data, all the things that your HTTP server returns as part of a request. So you can do processing based on return codes. You can do it on media types, document sizes. Anything that you get back from the HTTP server you can use as a qualifier when you're processing the archive. This is the design process. Start out like all great applications with a great idea. You build some code, you test some code, identify the pages or documents you'd like to process, schedule your job, you run your job, and you check the results, and then finally you publish the results either for your own use or for global use. The great idea is really up to you. These are some of the things that we've heard from other developers. Building vertical special purpose search engines, doing search engine optimization, doing search engine marketing. If you are in either the SEO or the SEM businesses, you might want to use this platform as an analysis tool to figure out where you stand relative to your competition, figure out what you're doing, what your competition's doing, and then figure out a way to do better than they are. We work with a number of different researchers that have various concepts, various theories they'd like to validate about the web. They can do that on our platform. But for the most part, we expect developers and entrepreneurs to come up with lots and lots of different great ideas for ways to use this platform. We'll be happy to talk with you afterward in private about your own ideas and bounce ideas off you if you'd like. So next you need to actually go ahead and write your code. So you write your code, you're actually writing your code on an interactive node at the Linux command line. So you're doing interactive application development. We have various APIs that you use while you're building that application. There's things like the collection API where you're pulling data from the archive. If you're pulling data and you want to then create new collections, let's say you're scanning every page, and every page you find that has your domain name on it, you'd like to write out into a separate collection for later processing by a second job, you could use our collection API. You can write your code in any language that's going to run in the Linux environment. We do have special support language libraries for C and for Java and for Perl, but literally any language that can read from standard in and write to standard out can be used on this platform. There's also an execution framework that's used to manage the multiple processes and multiple jobs and multiple CPUs that are involved in the computational process. And so when you build your application, it's really simple. You build an application such that it knows how to start up and process a single document. If you build it within the framework, then the framework will take care of running that application just once and then feeding it iteratively documents from the collection. So the application isn't literally started up afresh for each different document. But you simply write an application that knows how to do one document. It's handed off that one document. It has access to all of the document headers, and it can do any processing at once. It doesn't get you don't get anything pre-parsed. You simply get, here's a bunch of headers, here's the document, any parsing of XML, parsing of HTML, totally up to you. If you want to do some simple string scanning, look for various key phrases or terms in the return document, up to you. If you're processing image files and you're saying, let me look through every JPEG I can find on the web, that would be up to you to do any image processing that you'd like in there. We don't pre-process the data in any way. We simply hand it off to your application. So your code can look at the document. It can look at the headers. You can write out to new collections that you can use for further processing later on. You can write your results to standard out, and you can either do local storage in the user data store, or you can store your data to Amazon S3 if you have some long-term data storage requirements. All right, then you need to test your code. What you do, since you're going to be paying for CPU time at the point when you run your application, you want to make sure it's working in the small before you run it in the large or the gigantic. So you run a small test on an interactive node. To make this easier, we give you some predefined document collections that are lists of a couple hundred, a couple thousand documents a piece of some various representative types. You can get to these documents from the interactive nodes. It's really important to do your testing first. You want to make sure your application is doing what you expect, because we are in a batch processing mode and you will pay for CPU time. And one important thing you need to do is you need to figure out the efficiency of your application. Figure out, for each document I process, what is the approximate amount of real time I'm going to need to do that processing when I run on the compute nodes. You'll see when we go ahead and reserve CPUs, you actually need to reserve a certain number of processors for a certain amount of clock time. So it's really important that you reserve enough time for your application to do all the work it needs to do. There is actually a suspend and restart model if it doesn't finish within the allocated time, but the cleanest thing to do is simply reserve adequate time for your application to fully process. Okay, let's see if we can get this clicker to work. Okay, the next thing you need to do is figure out which pages in that archive you'd like to process. So you need to choose a crawl, the in-process crawl, the current crawl, or the historic crawl. And you do the actual specification of the pages you'd like to process using an interactive set of web pages. There's a whole lot of different ways you can specify those pages. You can say, I want to process everything within a particular domain name. You can go any number of levels deep within a particular domain. If you wanted to process everything inside of msdn.microsoft.com, you could choose that as the subject of your processing. You can say, I want to process pages that link to a certain domain or are linked to from a certain domain. You can say, I'd like to choose pages that are only within a given Alexa rank. So you could say, process the top 1,000, top 10,000 pages, pages that return a certain redirection status. Any HTTP header, you can actually filter the crawl in advance. You can even filter by content and say, I only want to filter pages that contain my name or my company's name. So you use a set of interactive pages. You define an object that is called a collection. And this collection serves as input to your actual processing when you're running on the compute nodes. Okay, we use a set of pages on alexa.com. It's actually at websearch.alexa.com is where you can learn a lot more about this. And we go through and we specify the collection that we'd like to process. There's a set of predefined collections you can use that are essentially the whole crawl. So for certain applications, if you simply want to inhale and process the entire 100 terabytes of data at once, you would do that with a predefined collection. But that's going to cost a fair amount of money, so you're probably going to want to be a little bit more specific. So first you can look at the public collections, and you can see we've got the first 3 listed up there are the full crawls, and then we have a few test documents in there, or test collections. So the in-process crawl, the one at the top, actually has about 1.9 billion documents. The in-process one's at the bottom. That's 1.2 billion documents. The full one, let's see, the EG one in the middle is 2.7 billion, and then the full one at the top is 1.9 billion. So there's quite a bit of content there. It pays literally for you to be as selective as possible in processing this data to choose exactly what you'd like to process. So what I did here, I decided I'd create a simple collection of all the documents that are linking to Microsoft.com. So I use the add to query function here. I'm going to build a search-based collection. The idea of a search-based collection is I'm specifying a set of search terms. Once those terms are in the system, every time that I access this collection, it's going to do a fresh search against the crawl and return all the things that are matching against there. I can also do a file-based collection that is more of a static concept. So a file-based collection, all of the processing is done up front, and then that actual set of documents to process remains static for the lifetime of my processing. So I'm going to find all the sites that link to Microsoft.com, and so that's my first step here. My second step, I'm going to say I only want to process documents that have the word Scoble in it. So maybe I'm Scoble's boss and I want to figure out how well is he doing at actually getting people to link to Microsoft. So I can define this collection. Once I get it in there, as I go through these steps, it's actually showing me on the page. You can see there over on the right, it says the current document size. So before I've actually put this restriction in, there's about 64 million documents linking to Amazon, or linking to Microsoft. I'll put the Scoble filter in there, and we'll save the search-based collection. And now I have it. Looks like there's about 64,599 documents in my collection. So what I'm doing here is I'm defining the set of things I'd like to process when I write my code to run on the compute nodes. I've got that collection defined. Next thing I need to do, I need to go ahead and schedule my job. So by scheduling a job, what am I doing? I'm allocating compute resources within the Alexa compute cluster. I need to allocate a certain amount of wall clock time, and then I need to allocate a certain number of processors. Right now, you can use up to 10 processors at a time, and if we see jobs that seem to be able to benefit from more than 10, we'll certainly scale up our infrastructure accordingly. We have a lot more than 10 processors available, but at this point, we can manage up to 10 per job. Each of the processors you get is a fairly powerful CPU. You get a 3.6 gigahertz CPU, 4 gigabytes of RAM, and then 500 gigabytes of local storage on that machine. You pay us for this usage at $1 per CPU hour. Now, if you wanted to, you could use this for your own processing that was wholly unrelated to Alexa. If you certainly only wanted to use it as a heavy-duty compute node, I don't think there's anything that we would do to stop you from doing that if you find this pricing effective. So you're going to schedule this job. So you're going to tell us how much time you need. And that's why I said it was really important for you to measure in advance how much time you need per document. So you're going to figure out what that time is. You're going to multiply that by the number of documents to process, add a little bit of room for just so everything's going to work. And then you schedule that amount of time. So you say, I need 5 processors for 2 hours, let's say. I need 10 processor hours. Use the created job page within the portal. You tell us information about which processing framework you're going to use, the name of your executable, where you want the output file stored. You want to tell us how we're going to put the output together. So we're going to run all these jobs in parallel, and we can either take all that output and just concatenate it together into one big output file. We can run it through a sorting step and then order it, and that's up to you. We can do that either way. You tell us which collection we're going to process, how many CPUs you need. Once we have that information, We then give you a schedule, and you look at the bottom right there, and it's showing you these are the 3 different times that we can schedule your job for. So based on your request and the resources that we have available to you, we can tell you this is when your job is able to run. So based on any other particular scheduling constraints you have, you can choose which time works best for you. There are some people that like to actually monitor their jobs interactively, so you might want to run it at a time that's convenient for you, so you can go in and look at log files and look at the progress as it happens. So you schedule your job. At that point, it's going to just take off and run at the appropriate time. As that job runs, it will have available to it the collections. It'll be running on the set of compute nodes that you specify. The execution framework already makes sure that we take that document collection, we dole it out fairly and evenly to all the different processors involved. If any of those processors happens to die for some reason, we'll restart the process on a different compute node. If we see that your application is simply not making any progress because things are dying again and again, we'll simply abandon the job rather than trying to burn CPU time forever. So you run this job. It's going to produce some results. So your job runs at the specified time. The framework is going to take care of copying your code off to all the different CPU instances, giving it the standard input of an allocated slice of a collection, monitoring each of the nodes. It actually monitors them to make sure that as the time is going forward, it's monitoring to make sure that it's actually making progress through the collection. As this is running, you can go to the portal. You can look at the number of documents that have been processed. You can see the intermediate log files, any temporary files that you're producing from the job. As the job finishes producing output, it's combined as you specified, either by concatenation or by sorting. And then finally, you store your results. And you can store those locally within your user data. You can store them as a new web search index, or you could store them within Amazon S3. How do you check your results? You might want to actually log in, and you can log into your interactive node, and from there you can log in and check the progress on the compute nodes. You'll get a final status email from the system at the point when your job has completed. When you build your application, it's probably a really good idea to actually generate some log files, so you know the progress, you can see any exceptions or any unusual things happening. And finally, you would want to monitor the output from your job to make sure you're getting what you expect from there. Because of this, it's a really good idea. You build your job, you try it on a small collection, make sure you're getting what you want, and then scale up to the full collection. Then finally, you publish your results. A couple different things you can do here. You can store raw data to Amazon S3 and then pay us for the storage. You can create a new search index. So let's say I was really concerned about how people use my name. So I wanted to go through and on every page on the web compute a thing I called the Jeff rank. So I could scan every page in the collection for people that mention my name or link to one of my sites. Once I find that, I could create a new search index, and I'll call it the Jeff rank index. I store that within the AWSP system, and then I can choose to publish that index. And so people doing searches using the Alexa web information system could actually then say, let me retrieve pages based on the Jeff rank of these pages. You can also publish data for access via a web search. You can put any kind of data schema you'd like on the output. And that data would then become available either only to you, or you could choose to open it up to a small group of friends, or you could open it up to the web at large. If you wanted to share that out to the world, you certainly have that ability with the system. So putting this all together, you have the ability to do things for a budget on the order of a couple $1,000s that if you were to build your own search engine from scratch would probably be probably close to a multi-million-dollar investment at this point. The amount of hardware you need, the amount of bandwidth you'll consume, the amount of processing power you need is simply not something you can do as a small unfunded startup at this point. If you want to prove out your concepts before you become that funded startup, this platform certainly gives you the ability to do that. We're working with a number of beta developers right now, seeing some pretty cool things built. I don't have anything I can share with you yet because a lot of the people doing fun things with this actually they're learning great properties about the web that they're so valuable what they've learned that they say, I'd better just keep this information for myself. One of the neat things about it's so competitive that you see that people are just kind of hiding the results. When we do things with the e-commerce system, for example, people are very, very happy to share out the results and show their cool online shopping applications and stores. But the various Alexa services they're so great at pulling in competitive data that we have to almost go out and pull teeth to get people to show us the cool things they've discovered about the web. That's about all I have ready to show you. I'd love to answer any questions, and if you have some more private things, we can certainly talk afterward. We've got 2 microphones, and best would be if you step up to a microphone and we can answer questions from there. No questions yet. Here we go.
Yeah, hi Jeff, Joe Hunkins. Could you talk about A9 and the relationship that's going to have to the rest of the Alexa services? Are they completely independent, or?
Okay, good question. So A9 is a consumer-facing search engine. One of the neat APIs that A9 has is something called the A9 OpenSearch API. That is something that was developed at A9, and we worked with the folks at Microsoft to allow other applications to call that API. So the A9 infrastructure and the Alexa infrastructure are logically and physically separate as far as I know. They're really meant to serve some different purposes.
Name's Reg Shrami. I run a blog, Web 2.0 Central, and I've got a startup that's interested in the search space. One of the questions I have is just what would a ballpark cost if we wanted to run the whole index? What kind of a order of magnitude are we looking at? Okay, so of course the answer is it depends on how much processing you want to do. My understanding is that to do a simple string scan of every HTML page in a current index is somewhere around a $2,000 investment. Great, thanks.
Okay. Okay, thank you for your time, and be happy to talk to you privately afterward.